This video has everything you need to know about gravitational potential energy for your GCSE. We're going to look at three main things in today's lesson. We're going to learn the equation for calculating the amount of energy in the gravitational potential store of an object. Then we're going to look at practicing a calculation using that equation. We'll look at rearranging the equation, and the final thing we'll do is probably the most complicated thing so far. It's going to combine the stuff we learned in kinetic energy with the stuff we're learning today about gravitational potential energy, and you're going to see what happens when an object high up falls, so its gravitational potential energy turns into the kinetic energy and allows us to calculate the speed that the object hits the ground at. The first thing we want to have a look at is what is gravitational potential energy. Now, it's basically the energy an object has because of its position in a gravitational field. We'll do all our examples today with a 1 kilogram bag of pasta. So this has a mass of 1 kilogram, but depending on where it is in the Earth's gravitational field, it has a different amount of gravitational potential energy. Now, the higher up it is in the Earth's gravitational field, the more energy it has in its gravitational potential store, and the lower it is, the less energy it has in its gravitational potential store. Let's now have a look at actually how we would calculate the amount of energy by learning the equation. Now, obviously it's going to have mass in it, and it's also going to have the height in the equation, because the higher it is, the more energy it's got in its gravitational potential store. The other thing that was in the definition that we were talking about was that it's to do with the position in the gravitational field. So depending on the strength of that gravitational field, the energy will also have a different amount in the gravitational store. Right, let's have a look over here then. Gravitational potential energy is equal to, we'll start with the mass of the object. Then we're going to put in the gravitational field strength. Gravitational field strength. So on Earth, gravitational field strength is 9.8 newtons per kilogram. I'm going to put the units under here, newtons per kilogram. And the specification says this, and I've emailed AQA and they've confirmed that they will always give you the value for the gravitational field strength in the question. So you don't have to learn any of these ones, you're just going to be putting that into the equation. And the final factor here is the height. Let's do the rest of the units. Height is going to be measured in meters, and mass is obviously going to be in kilograms, and gravitational potential energy, capital J for joules. Okay, there are units done. Let's stick it in symbols as well. This is how I would always remember my equations. So EP, so energy in the gravitational potential store. In the last lesson we had EK, so we're doing EP here. We've got M, G, H. So M for mass, G for gravitational field strength, and H for the height of the object in that gravitational field. One extra thing here that you might want to factor in, especially if you go in the top grades, mass times gravity is actually the weight of the object. You probably learned that at Key Stage 3. So another way of kind of writing this, since mass times gravity is the weight, you've actually got the gravitational potential energy is equal to the weight times the height. You might want to add that into your notes as well. So the stronger gravity is, I'm just going to note this one down just so you know this one. On Earth, G, the gravitational field strength, is 9.8 newtons per kilogram. What does that mean? Well, if this is 1 kilogram, it means when I pick it up, I feel a force of 9.8 newtons. I pick that up, that's a force of 9.8 newtons pushing down on my hand now. If I went to the moon or something, where its gravity 6 times less, then that G would only be 1.6 newtons per kilogram. Right, we've got the equation, that's our AO1 knowledge done. We know the equation, we know all the units. Let's look at applying that now. Let's get our AO2 skills sorted. We're going to look at putting energy into the gravitational potential store of this bag of pasta. If I put it on the floor here, we're going to say that it has 0 energy in its gravitational potential store. So if this is its gravitational potential store over here, it's got 0 energy in it. Now, as I go to lift this up, so it's going to gain energy in its gravitational potential store. The energy is going to start to move into the gravitational potential store. Every time I lift this up, it's going to get more and more energy in the gravitational potential store. Okay, and then finally, when we put it right up at the top, it's going to have even more gravitational potential. Now, what we need to do to get this equation actually working is we know the mass. So over here, we know the mass is 1 kilogram. We know the gravitational field strength is 9.8 because we're on Earth. So we just need to measure the height. Let's have a look at using that then with this tape measure. So what this is showing that you need to. There's 2 potential errors when you're measuring the length of something. There's a parallax error if I don't line the camera up properly, or in most cases my eye with the measuring scale. And the other one is you need to keep the ruler vertical, so you do something like a set square to check that that is actually vertical. And we get a height of, basically if I lift it just above the shelves, 150 centimetres. Let's now put the numbers into our equation. So we've got how much energy have we put in our bag of pasta. Well, we've got a mass of, well, I'm going to write it out again here, mgh. So our mass is 1 kilogram. G, 9.8 on Earth, 9.8 newtons on every kilogram. And H, with 150 centimetres. So that is going to be, again, centimetres, we're looking at conversions. Centi is 100th, so we've got 100 divided by 150, or 1.5. We put those together, I'm just going to get my calculator. Let's have a look. So 9.8 times 1.5 times 1 gives us 14.7 joules. So it's as easy as that for calculating the amount of energy in the gravitational potential store. So that energy has gone into the gravitational potential store. One little question, I guess, though, is that you always need to be able to describe the changes in energy stores when anything within a system moves. So obviously we've got energy coming into the gravitational potential store, 14.7 joules worth. Where's that energy come from if we can't just create it? Energy's got to be transferred from somewhere. So where it's actually come from is the chemical store within my muscles. So as you pick up that object, the energy is moving from the chemical store of the muscles into the gravitational potential store. So we've still got the total amount of energy within the system being the same. Eventually, you've lost that energy from your chemical store and it's gone into the gravitational potential store. Let's look at a couple of ways in which the examiners could make this a bit trickier rather than just putting the numbers straight into here. Obviously, the first thing that they could do is put this into grams instead of just putting it in kilograms. So we could have done this with a can of baked beans or something, like 450 grams, so you'd have put 0.45 kilograms. We've already done this one, converting from centimetres, put that into metres. The next ones involve, let's look at what if they gave us the energy instead, and then we have to try and work out how high it's moved. Right, in the rearrangement scenario, the examiner is going to tell us we've got the same 1 kilogram bag of pasta, but this time they're going to say we've got 3.92 joules of energy in its gravitational potential store. So how high has that object been lifted to put that amount of energy in its gravitational potential store? Let's have a look. We'll start with the equation. So anytime they say calculate, you just say, I'm going to write down an equation. So we've got mgh. This time, they've said 3.92 joules in the gravitational potential store. We've still got 1 kilogram. 9.8 is gravity on Earth, and therefore we've only got one unknown, which is h in our equation. We're going to divide by our 1, which is essentially just 3.92 still, and we're going to divide by 9.8 to get rid of this times 9.8. So we'll have 3.92 divided by 9.8 equals the height. And just do that again quickly on the calculator. So 3.92 divided by 9.8 gives us 0.4. So h that time is 0.4, and that'll be meters. 0.4 meters, well, that's going to be on here, the height from there. So that's the equivalent of you lifting that bag of pasta and just putting it one shelf up. So we're just placing it up to there, and that's how much energy has gone into the gravitational store. If it said that the energy had decreased by 3.92, that would mean it's come from a higher shelf down by 40 centimetres. So it's gone down that far instead, because the energy's come out of the gravitational potential store. The final thing we've got to do today then is the most mathematically involved, but it allows us to answer all kinds of questions. It's essentially saying, if I have this object here with energy in its gravitational potential store, so we looked here and said, okay, it's got 3.92 joules of energy in its gravitational potential store. What would happen if I then dropped it onto the floor? So it's lost that energy from its gravitational potential store, and that's been transferred into another store. It's gone into its kinetic store. So that just before it hits the ground, all the energy's moved from the gravitational potential to the kinetic store. Let's have a look at how we'd go about solving that. And we're going to be able to calculate the speed that the pasta hits the floor at. I think it's worth going over this a couple of times just to make sure we got the concept in our head. So we look at the pasta one first. And we're going to start with the object on the shelf up here. And we'll do our graph over on the other side. We'll have EP, and that has got a bar 3.92 joules high, and EK has got 0 energy in it. Okay, now what's going to happen is the pasta is going to fall onto the floor, so that height difference there is 0.4 meters, and the pasta falls onto the floor. Okay, so at the end, when we're looking at our energy story, the potential energy will be 0, and the kinetic energy will have all of that energy put into it, so that would be 3.92 joules. The idea is then that the energy is moved from the potential store into the kinetic store. So now we can work out the speed that it hits the ground at by remembering our equation for the energy in the kinetic store. So the kinetic energy, that will be the same as the potential energy it had at the start. So that will be 3.92. The mass is 1. We want to work out the velocity, so we don't know that, we'll leave it as v, and we've got to remember to divide by 2. Okay, let's use our calculator to sort us out with the answer here. We've got to times by 2 here, so we've got 2 times 3.92. That'll give us 7.84 is equal to 1 times v squared, which is just v squared. So then, to find out v, all we've got to do is square root 7.84. So if I press my square root button, we get v equals 2.8 meters per second. The principle behind this, to solve this, now there's a little bit of maths involved here just to find the unknown, which is v, or v squared, again then square root it. The concept, the principle underlying this is that energy can never be created or destroyed. So if it had 3.92 joules in its gravitational potential store, and that decreases to 0, that energy's got to transfer into a different store, and it's gone into the kinetic store over here. So that's our EK and that's our EP. Because this is one of the most complicated things in this entire section on energy, we're going to do one more example of this. We're going to calculate the speed which I come off the end of a slide. So I'll go up to the top of the slide down it, and we'll calculate the velocity of which I come out off the bottom of the slide. First, we'll set up the theory for you to be able to see. So there's me up here, and then I'm going to go down to here. Now the height of here we'll call h, and we're going to try and work out my velocity at the bottom. We're going to need to know a couple of things, which would be the mass of me, and so I'll tell you my mass being 80 kilograms. And the principle, again, all you really have to understand is this principle, and then it's just remembering the equations and putting the numbers in. The principle is whatever energy I have in my gravitational potential store will be transferred into my kinetic store at the bottom, because I can't go down any further in height. So all the energy from my potential store has gone into my kinetic store. So look at how we do that. We've got our potential, mgh, and then we've got our kinetic at the bottom, ek, mv squared over 2. The height in here is 120 centimetres, so that's 1.2 metres. So we can easily work out the mgh at the top. So my mass times gravity on Earth, 9.8. Again, remember that, we'll say that in the question, times 1.2. So that gives us 940.8 joules. Now what I'm going to do is go outside and slide down that slide, turn all of my gravitational potential energy into kinetic energy as I slide off the end, and then we'll come back and calculate how fast it is that I slide off the end there. Right, let's have a look at calculating how fast I actually flew off that slide just using physics and maths. We're going to say that at the top of the slide I had this much energy in my gravitational potential store. That's going to transfer into the kinetic store by the time I get to the bottom. So in this equation here I can put 940.8 equals to my mass, which is 80, times v squared, so that's what we don't know, trying to work out the velocity I hit the end of the slide with, and divide it by 2. We'll do 940.8, times it by 2 to get rid of that, divide by 2, and then divide by 80 to get rid of there, and I get 23.52, that's v squared. So now all I need to do is square root that to get v. So v would be equal to 4.8 meters per second. Does that seem reasonable? Again, yeah, it seems like shut off there about roughly 5 meters per second if we flew off the bottom of there. Now that we've done the maths, we've done our AO1 skills, which is recording the equation and the units. AO2, we've applied this in 2 different scenarios. There's now an AO3, an analysis or an evaluation section to this question, which is the speed actually as much as that? Now thinking about this, we've said at the start, all the energy was in the potential store. Then at the end, we've said the potential store had 0 and the kinetic store had all of that energy, okay, all 940. But in actual fact, there's a lot of friction as I slide along the slide, and that's going to basically use a force with mechanical working to transfer some of that energy into the thermal store So that will have gained some of the energy, and therefore there won't have been quite as much in my kinetic store. If there's not as much in my kinetic store, I won't have reached such a fast velocity at the bottom. So there's work done, mechanical work done by the force of friction, transferring some of that kinetic energy into the thermal store, so I'm not going to have that speed, not quite as much as that at the bottom of the slide. A final thing I'll do with you is just to say, it's great if everyone can follow those parts, but some of you might be able to take the next step, which is to work out, this is a great thing about physics, you can work out the speed anything has when it hits the ground just by knowing how high it is from the ground. So I could put this bag of pasta any height, say up there, so that's 1.5 meters off the ground. How fast will it hit the ground? I can do that really simply. Let's have a quick look at this. The principle we've been applying is that the kinetic comes from the potential, the gravitational potential. So we've got here mv squared over 2, and that's equal to mgh. Well, the m's on both sides, so I can just cancel that off. And so actually I end up with v squared on this side. If I times by 2, I'd get v squared is 2gh. So therefore v is equal to the square root of 2gh. So just quickly, you can work out the speed that pasta hits the ground. Don't need to know the mass of the pasta even. Just have to go 2 times 9.8 times 1.5 and square root it. Let's just see how fast I would actually hit the ground at. We've got 9.8 times 2 times by 1.5 square root, and it'll hit the ground at 5.4 meters per second. And that's the magic of physics. You can do all these real world problems so easily. You can do stuff like a pea shooting off the Eiffel Tower, that's a question in the workbook, and you can do all this so simply and work out the speed anything hits the ground at there, just using the conservation of energy. Now you know everything there is to know about gravitational potential energy. You know the equation, you can apply it, rearrange it, and you can use energy conservation to combine energy moving from the gravitational potential store to the kinetic store and work out the final velocity something's travelling at. You can also now be aware of the subtle point that that's the maximum velocity, and that in real life the velocity will be a little bit less than that because some of the energy will have been transferred into the thermal store of the object and the surroundings, increasing the temperature of those objects slightly. Right, we'll move on to the next video and keep doing your practice questions and let me know if you've got any questions. Just wait out there boys for a minute.
Cool.
You just playing there? I've just got a few more things. Would you want your Power Rangers?
Yeah. I didn't know you were going to do it in here.